Hello, I'm Jumpei Goto. Today, I'm going to talk about our work, learning intra-class multimodal distributions with orthonormal matrices. First, I would like to introduce the motivation of our work. In this study, we focused on classification tasks with deep neural networks. Conventional classification models using deep neural networks extract feature vectors from backbone networks and give features to linear classifiers. The linear classifier assigns a single weight vector to each class and identifies the category by comparing the scores obtained from the similarity between the weight vectors and feature vectors. Since feature vectors get close to the weight vectors during training, learned features tend to be distributed unimodally, which makes it difficult to represent intra-class variations such as color or brightness or texture. To tackle this difficulty, an online clustering method, so-called Deep Nearest Centroids method, was proposed. Deep Nearest Centroids (DNC) prepares k subcentroids for each class. To compute the classification scores, DNC uses the maximum similarity between feature vectors and the subcentroids. DNC updates model weights and subcentroids alternately with different strategies, gradient-based methods, and online clustering. However, the alternating updates with different strategies can be unbalanced because the step size of model weight can be much smaller or much larger than that of subcentroids. In addition, to conduct online clustering in each iteration, DNC costs huge memory to store past features. To overcome these challenges, we replace subcentroids with a weight matrix to avoid online clustering. DNC logit function can be expressed as similarity between feature vector Z and WA, where W is a weight matrix and A is a discrete assignment vector. By relaxing the discrete assignment vector to continuous one, we can apply gradient-based method instead of online clustering to update weight matrix. Then, how do we determine the appropriate assignment vector? To determine the assignment vector, we impose orthonormal constraints to weight matrix. By imposing orthonormal constraint and using L2 norm as similarity measure, we can utilize the optimal assignment vector, which minimizes the L2 distance between the feature vector Z and WA. Orthonormal constraint can be satisfied by applying Riemannian stochastic gradient descent method. So we can update model weights and orthonormal weight matrices simultaneously using a gradient-based method. To evaluate the performance and effectiveness of our method, we conduct classification and cost-to-fine experiments. In the classification experiment, we use CIFAR and ImageNet datasets. As the table shows, our method achieves accuracy improvements on CIFAR 100 and ImageNet. In addition, the TSNE visualization shows that our method can capture final representations, such as a bird perching on a branch. In the cost-to-fine experiment, we trained models using coarse-grained labels and evaluate them on fine-grained labels using nearest neighbor classifiers. The experimental results show that our method gets higher accuracy on both coarse and fine-grained labels. Additionally, our method obtains a large margin among the fine-grained categories by training with coarse-grained labels. That's all. Thank you for listening.